So today we're going to be going over chapter 3, where we talk about landscapes that are being fashioned by water. And in this chapter, we're going to be talking about water both on the surface of the earth, things like rivers, oceans, and lakes, as well as water that's inside of the earth as well. But when we're talking about water, the first thing that we really need to talk about is what's called a reservoir. Now, a reservoir is basically just a place where water is being held. But water doesn't just stay in one place or in one reservoir. It's constantly moving from one reservoir to another through what's called our hydrologic cycle, or in simpler terms, the water cycle. So in this hydrologic cycle, again, we're just moving water around from one reservoir to another. But there are a lot of different reservoirs found on our Earth, and these reservoirs all hold very different amounts of water. So here we see a list of our major reservoirs around the Earth. And as we go from the top to the bottom of this list, we're going from larger to smaller reservoirs. So on Earth, the largest reservoir is the ocean. We're going to see that almost 3/4 of all the water on our planet is found in our oceans. But if we're looking for water that we can drink, we know that we can't drink salt water. If we're stuck in the middle of the ocean for a prolonged period of time and we start drinking that salt water, we're very quickly going to get dehydrated and it's going to do some real damage to our bodies. So as humans, we're very concerned with finding fresh water, water that doesn't have all that dissolved salt inside of it. So the rest of these reservoirs are freshwater reservoirs. And again, that just means it's not a salty water. It's safe to drink. So the second largest reservoir on our planet are glaciers. And glaciers are just massive chunks of ice. So think about Antarctica or Greenland, some of the largest glaciers on our planet. But when water is stuck within glaciers, it's actually stuck. It's not going to be able to move to another reservoir until that glacier melts back into liquid water. So again, as humans, we're concerned with finding fresh water that we can drink. It'd be very difficult for us to go to Antarctica, get a big chunk of ice, and then bring it back to Florida to have drinking water. So we want to not only find fresh water to drink, we want to find accessible fresh water. That means that we want it to be nearby, and we also want it to be very easy to access, which is a good thing for our third largest reservoir, which are our rivers, which we'll be talking about pretty substantially within this chapter. We've all seen rivers before. It's just water flowing from one area to another. But eventually, all of our rivers end up emptying out into our oceans. Here in Central Florida, we also see a lot of lakes, which is a large proportion of this hydrologic cycle. And lakes are different from rivers because generally in our lakes, the water's sitting still. It's not flowing from one area to another. But now that as we're moving farther down this list of our reservoirs, we're getting into smaller and smaller amounts of water on our planet. So when we're talking about air, air has water inside of it, but now this water is in a form of gas, not a liquid or a solid water. So even though we can't see the water inside of our air, it's really important. It helps keeps our lungs moisturized, our skin moisturized. So even though this is kind of invisible water, it's still a really important proponent on our planet. Another type of water that we're going to be talking about today is going to be groundwater, or water that's stored below ground on our planet. So these are going to be different types of water that are stored either in solid rock or in just loose soil. Think about the dirt outside in your yard. But both rock and soil hold a little bit of water inside of them. And then finally, our smallest reservoir on the earth are living tissues. So think about our bodies. We're like 70% water. So if we look at all living organisms on our planet, from humans down to insects, there is a lot of water stored inside of all of us. But this water is not really accessible. I personally don't really want to drink water that came from someone else's body. So when we're looking for drinking water on our planet, and we're going to be discussing this a lot in this chapter, there are two things that we need. We need fresh water. It needs to not have a lot of dissolved salts, and it also has to be accessible. It needs to be water that's nearby, and very easy and cheap to access. But water doesn't just sit in one reservoir. It's constantly moving from one reservoir to another through this hydrologic cycle. And I'm sure that all of you have seen the water cycle in some science class or another throughout your education. Sometimes we're just going to be moving liquid water from one area to another. But a lot of the time in this hydrologic cycle, we have to change the state of water. And this simply just means changing it from, let's say, a solid to a liquid, or from a liquid to a gas. But our hydrologic cycle is going to follow three main parts. It's always going to start off in our oceans. Oceans cover almost 3/4 of the surface of our planet. So this is a huge amount of area where sunlight is hitting the surface waters. As the sunlight hits the first few feet of the water, it's going to heat it up pretty rapidly. And we know that as we start heating up water, it very quickly changes from a liquid to a gas through a process called evaporation. So we generally see that our hydrologic cycle starts in our oceans. Here, this water is going to be heated up and it's going to evaporate. It's going to change into a gas form of water that's going to sit inside of our air. But if we have enough of this gaseous water in our air, eventually it's going to condense into clouds. And clouds can only hold a certain amount of water. Once they're full of water, we're going to see precipitation occur. And here in Florida, it's almost always very warm, so our precipitation is most often some form of rain. But if we lived in a colder environment, we would see a lot of different other types of precipitation, such as snow, hail, and even some of these odder ones like rime or graupel. But once we have precipitation occurring, we are transferring all of that water from our air back down to the surface of our planet. And on our surface, we have a lot of ground cover. We have grasses, rocks, and roads that cover the surface of our planet. So we're going to see that some water, some precipitation that hits our surface is going to infiltrate or basically be absorbed inside of our ground. But only a small proportion of the water is going to infiltrate below ground. The rest is going to run off. It's literally going to run along the surface of the planet, usually through rivers, until eventually it's discharged back into the ocean, where this cycle is just going to begin again. So when we look at all of the water on our planet, we want to look at the proportions of water and where it's stored. So overall, almost 97% of all of the water on our planet is found inside of our oceans. So almost all the water is water that we can't safely drink. So again, as humans, we're always concerned with finding safe water to drink. So now we need to look at this 3.5% that's not salt water, that 3.5% of water that is fresh water. So even though 3.5% is not a lot of water overall, it's enough to keep all living forms hydrated and alive on our planet. But if we look at our second largest reservoir, again, it's glaciers, that water that's stored as solid ice. And here it's not even 2% of all of the water that's stored within glaciers. Our next largest reservoir is groundwater, that water that's stored below ground in rocks and soils. And here this groundwater makes up less than 1% of all of the planet's water. But here in Florida, a large proportion of our drinking water, so if we just turn on the tap, that water is coming from beneath our ground as groundwater. Not every place has groundwater though. So if we were to live in another area besides Central Florida, it's likely that we would get our drinking water from surface water. This surface water just means water sitting on the surface. So it's going to be things like lakes and rivers. And then our smallest proportion of water is going to be the water inside of our atmosphere, the water in our air that we can't physically see. So this entire hydrologic cycle is powered by our sun. The sun is incredibly hot. So when we see the sun's rays, it's not only bringing light, but it's bringing heat with it. So again, this hydrologic cycle starts off in our oceans. All of that intense heat coming from the sun is going to cause evaporation of our oceans. And eventually, all of that evaporated water is going to end up in our atmosphere, generally condensing into clouds that will eventually form precipitation, some form of water falling from the sky back down to the surface. Generally, we think of precipitation as always being rain, but this is incorrect. When we get further along into the semester, we'll see that there are 9 major forms of precipitation, and rain is only one of those 9. But this precipitation is important because it's completing this hydrologic cycle. Again, we're taking all of the liquid water inside of our oceans and then transforming it into a gas form of water inside of our air. But air can only hold a certain amount of water. Eventually, that air is going to be saturated. It's going to be holding as much water as it can physically hold. So think about if I can only hold 100 pounds. Let's say I pick up a 100-pound weight, and then someone else comes along and puts another 20-pound weight on top of it. I physically would not be able to hold that weight. So I would probably just instantly drop all of the weight that I'm holding. And we see that our atmosphere does the exact same thing. Once our atmosphere is saturated, it's holding all of the water it can hold. If any more water is added, we're going to see that basically the sky is just going to start dumping all the water. It can't physically hold it because it weighs too much. So we're going to see precipitation occurring. And this precipitation is taking all of that gaseous form of water and returning it back to our surface. Again, either as a liquid or a solid. But eventually, all of that precipitation makes its way back out to our oceans, where we're going to see another part of our hydrologic cycle starting again. That sun's going to heat it up, and we're going to see evaporation. So with this hydrologic cycle, it's continuously happening. As long as we have a sun that's producing a lot of heat, we will continuously be transferring water around from one reservoir to another along the Earth. So after precipitation occurs, again, we're going to see that some of that water is going to soak into the ground through a process called infiltration. And we see this after every rainstorm. We're going to see that our grass is going to first start absorbing some of this water, but eventually that water is not just going to sit inside of our soil. It's going to keep moving farther and farther down inside of the earth until eventually it reaches the rocks beneath it. But overall, only a very small percentage of this precipitation is going to be infiltrated. The majority of precipitation instead is going to be runoff. It's going to be water that flows across the surface. This can either be a natural forming river, or if you've ever been on I-4 during a major rainstorm, you'll see that little streams of water will start forming and flowing across the road. This is also runoff. So with runoff, any form of water that's just moving across the surface of the earth. But we saw that our living organisms also make up a decent amount of the water on our planet, and especially if we look at plants. So plants not only absorb water from the ground through a process that's called transpiration, but plants also lose water. So think about a very hot day. If we go outside, we're probably going to sweat. Our body is going to start releasing some of the water. We're going to see that plants do a very similar thing. On a really hot afternoon, these plants are trying to keep themselves cool. So we see evaporation occurring from the leaves of our plants. So if we combine the plants absorbing water from their roots through transpiration and the water that's being evaporated from their leaves, this is a process called evapotranspiration. And it's just combining both the transpiration of that plant absorbing water and the evaporation of the plant losing water. But just to repeat myself one more time, precipitation is not always rain. If we have precipitation occurring in a really cold area like Antarctica, it's generally not going to fall as rain, but instead it's going to form some type of solid precipitation instead. And because it's so cold, that solid precipitation is going to stay a solid. And eventually it's going to form glaciers. And within these glaciers, the water is actually stuck. It can't move around to another reservoir until that glacier melts and that water returns to liquid water. So over time, we will see that our hydrologic cycle is balanced. This means that the amount of evaporation over our oceans equals out the amount of precipitation that occurs. But the water on our planet doesn't really change that much over time. So the water that we drink today is also the water that was around millions of years ago when the dinosaurs were around. But this hydrologic cycle is constantly just transferring water from one reservoir to another. But if we look at the differences between our oceans and our land, we're going to see that over our oceans, we see much more evaporation than we see precipitation. And that's because we have sunlight hitting the surface of our oceans. It's going to get really hot and it's going to begin evaporating. If we look at our land, where it's just covered in rocks for the most part, here these rocks don't hold a lot of water. So not a lot of evaporation occurs over land. But we'll see that on our land, we see more precipitation occurring instead. All of the water that evaporates from our ocean is generally going to be precipitated over our land. And then that water is just going to run off back to the oceans. So if we want to determine whether the precipitation that hits the land is going to infiltrate and be absorbed or just run off along the surface, there are a lot of different factors that are going to affect this. The first is just going to be how intense and how long did it rain. We'll see that if it's just a short afternoon sprinkle, the majority of that water is going to be infiltrated or be absorbed by the ground. But if we're talking about like a hurricane, where it's just going to be downpouring for days upon days, generally we're going to see more runoff occurring because the ground can only absorb a certain amount of water before runoff begins forming. And this is because the amount of water that's already in our soil is going to be very important. Soils can only hold a certain amount of water. So once the soil is full, the rest of the rainfall has to be run off. It's just simply going to flow along the surface of our planet. But our surface material, whatever is covering the surface, is also going to be very important. And we'll see this a lot in our cities. When it rains in like our backyard, generally it's just going to be a lot of grass and maybe different types of plants. Those plants, and especially their roots, are going to start absorbing or infiltrating the water. But if we go to a downtown area where the surface is covered in cement and concrete, here the water cannot infiltrate these types of materials. So instead we'll have more runoff instead. And we'll talk about this more later, but we generally see that flooding is a lot more of an issue in an urban area than it is in like a rural farmland. But another really important part of our runoff depends on the slope of the land. So if we were on campus and went outside of the parking lot, our parking lots are almost perfectly flat. So when we see really flat land, we're going to see more infiltration and less runoff. But if we start looking at steeper gradients, instead we're going to very steep gradients, now the water is going to be able to start flowing down the surface. And the steeper our gradient is, the faster the water is going to flow. So the steeper slope means that we're going to have less infiltration and more runoff along the surface. And then finally, the extent and types of our vegetation are going to be really important. If we just have a lot of different types of vegetation, let's say we go into a forest, it's going to be able to absorb more water than if we were just looking at a grassy field. But the type of vegetation is also important. We'll see that different types of plants need very different amounts of water in order to grow. So if it rained in a forest, these really big green trees are going to be able to absorb a lot of that water, leading to less runoff. But if we were to go to a desert environment where it's mostly a cactus that might be around, cacti need very little water, so they're not going to absorb very much, meaning that more runoff will occur in a desert than in a forest environment. So now we're going to transition into stream flow. And with stream flow, just think about a river that's flowing from one area to another. So when we're looking at how water moves within our streams or our rivers, water is going to be moving in two different ways. The first of which is called a laminar flow. And we see it here in part A of this diagram. You'll see that the water just flows in these nice, flat, smooth, parallel lines. When we look at laminar flow, it's going to look like the water is not even moving at all. It's going to be a river where it looks like the water is just sitting still. So in a face-to-face class, I generally like to show a YouTube video where a water balloon is filled with water and then it's punctured. Once we see the water coming out of this balloon, it is a laminar flow. If we were to look at the water kind of squirting out of that balloon, it's going to look like it's solid. We're not going to be able to see the water actually flowing if we look closely at the stream. But this isn't the most common type of stream flow. Instead, most stream flow is turbulent. This just means that the water is just moving around erratically. It's moving in all possible directions, just trying to get out of the area. And we see a turbulent flow down here in part B. Now it's not these nice smooth layers of water moving through. Instead, the water is just moving every possible direction, trying to quickly get out of that area. And we'll see that some of the water is going to be coming down and hitting the stream bed, kind of that kind of dirt layer of our rivers. But as the water hits our stream bed, it's going to pick up some of the sediment and carry it off in the water with it. So as we go from very slow moving to very fast moving waters, we're going to go from laminar to turbulent flow. And as we get into more quickly moving waters, it's just going to continue increasing the turbidity. So if you've ever seen a video of a flooded region, the water that's quickly moving through an area is going to be very turbid. You're going to be able to see that water just mixing about. And here we're just looking at two images of stream flow. If we look at the very front of this image here on A, we'll see that the river looks like it's not even moving. It's still moving, but this is an example of that laminar flow, where the water is moving in those nice straight layers from one area to another. In the middle of this image, we'll see that we can actually see the water moving. And that's more of a turbulent flow. And this is because we see these rocks sticking out. When water comes through and hits a rock, it's going to have to flow around the rock. So it's going to create a turbulent flow. But again, as we increase the velocity or how quickly that water is flowing through an area, we increase the turbulence. So a really extreme example of turbulence is looking at a whitewater rapid. Here in this image, we can see how rough this water is. This is just showing us how quickly it's actually moving. But there are a lot of different factors that are going to affect how quickly this water flows, which in geology we call the flow velocity. So this flow velocity is going to depend on a lot of different things. The first is just what is the slope or the gradient of the river channel. So if we have a very flat stream, we're going to see that it's going to be a very slow moving river. But if we have a really steep gradient, now our water is going to flow down that stream very, very quickly. So think about if I just want to take my bike out in two different locations. Let's say that I want to go to campus and just ride my bike in the parking lot where it's very flat. I'm not going to be able to go very fast on this parking lot. But if I find a really steep hill nearby, get my bike up to the top and then start rolling down, Very quickly, I'm going to start flying down a steep hill. So the steeper our slope or our gradient is of that river channel, the faster the water is going to move, or the higher the flow velocity will be. But we also need to look at how rough the channel is. So if we have a river where the bottom is just covered in really fine sediments, just really smooth, small pieces of dirt, that's going to be a very smooth channel. And here the water is just going to be able to slide right on top of it. So we're going to see that smooth channels move quickly. But if we have very rough channels, if we have a bunch of rocks that are just jutting out of the water, it's going to slow that water down because again, the water is going to come through and hit a rock, and then have to move around it to continue. So rougher channels mean that the water moves more slowly, or it has a lower flow velocity. And then finally, our flow velocity is going to depend on just how much water is inside of that channel. If we're looking at one river, on a normal day when it's holding just a normal amount of water, it might be moving relatively slowly. But let's say that we have a flood occur. Now this river is going to be holding 3 times as much water as it normally does. Now that we've increased the amount of water inside of our channel, that water is going to start moving more and more quickly. So the more water that we have in our channel, the faster it's going to flow, or the higher its flow velocity will be. So with our gradient, again, this is just the slope of the river channel. And when we're looking at our streams, we want to look at a profile. If we could cut a river in half and be able to look at it from where it starts to where that river eventually ends, this is going to give us a profile of our river. And almost every single river is going to have the same profile. We're going to see that in the headwaters, where the rivers initially form, this is usually going to be a very mountainous region. And when we think about mountains, we're going to think about really steep slopes. But as we move from our headwaters to those mountainous areas where the rivers form, we're going to start going from a very steep mountainous slope. And then as we make our way out to the mouth, where the river is going to discharge inside of an ocean, we're going to see that our slope starts getting flatter and flatter. But overall, the gradient of our river channel is going to determine not only how quickly the water is going to flow, but how much energy that water has as well. So let's go back to my bike example. If I'm trying to ride my bike around the parking lot, I am not going to be able to get a lot of energy. If I stop pedaling, I'm very quickly going to just come to a complete halt. But let's say I go to San Francisco and now I get up on top of one of those really steep hills. Now I don't even need to pedal going down these hills. Because I'm moving down a really steep hill, I'm just going to fly down the side of that hill. So we're going to see that steeper gradients provide more energy. And the more energy something has, the more quickly it's going to be able to move. So think about going on a run. If you do it after a long day of work, you're probably not going to be very fast. But if you do it in the morning when you have a lot of energy, maybe even after a pre-workout, you're going to have a ton of energy and you're going to be able to move more quickly. And water works in the exact same way. But again, we also have to think about how rough or how smooth our channel is. Because water is flowing over dirt and rocks along our channel bed. So everything along our channel is going to be producing friction. It's going to start slowing that water down. So if we look at a really smooth area, like our mouth, here it's smooth. So the water is just going to glide over it. But if we look at a rougher area, like in our headwaters, those really mountainous, steep regions, we're going to have a bunch of rocks just sitting in our bed channel. And again, the more rough, the more big rocks that we have along our channel bed, it's going to create more friction. It's going to slow that water down because the water now has to move around all of these rocks instead of just being able to glide over it. So one important term that we need to think about when we're talking about how quickly rivers flow is something called a discharge. And discharge is the volume of water that's coming out generally every single second. So this is not only telling you the amount or the volume of water that's flowing past, but it's also telling you how quickly that water is. But if we were to look at our rivers or our streams from where they start, again called the headwaters, and then where they end, called the mouth of the river, we're going to see this longitudinal profile. We're going to see that the shape of our streams change from where they start to where they end. So when I'm talking about the stream profile, this generally isn't just a few miles worth of the river. It is the entire river. So think about the Mississippi River. It crosses dozens of states. It's going to start out in a mountainous region and then end up dumping all that water in around New Orleans. So these streams cover thousands of miles, but they almost always start in a mountainous headwater and then they end along the beach at the mouth. But we're going to see that the overall shape of this profile is going to be almost the same regardless of what river we're actually looking at. And this is just called a concave curve. It's a curve that's dipping down in the middle. But we're going to see that different factors of our river are going to change as we look at different areas of the stream. So for this class, I just want to focus on the differences between the headwaters, where it starts, and the mouth, where it ends, because this is the two extremes of our different parts of our river systems. So we're going to see that when we start off along our headwaters, this is where the gradient is going to be the steepest. Those mountainous regions, we're going to have really steep slopes. And we know that steep slopes, that water is going to be moving very quickly down the side. Therefore, it's going to have a high flow velocity. But we're also going to see that we have large sediment sizes inside of these headwaters. If you've ever seen a mountain stream, they're just full of these giant rocks, sometimes as big as boulders. So here, because we have these large sediments, these large rocks, we're also going to have high channel roughness in our headwaters. When we get out to our mouth, now we have a very gentle gradient. It's almost flat, which means that the water isn't moving as quickly, and we generally have smaller sediment sizes. We're going to be moving down to sediment that's called clays and silts. It's so small that it's basically going to feel like mud if you touch it. And because now we're looking into really small sizes of sediments, we're going to have a very smooth channel. So overall, as we move from our headwaters to the mouth, we're going to see that our gradient, the slope, the sediment size, and therefore the channel roughness are all going to decrease from our headwaters to our mouth. But we're also going to see the exact opposite occurring when we look at our discharge and the channel size. So again, the discharge is just how much water is moving through every single second. In our headwaters, these are generally very small channels. Where I grew up, there was a river near my backyard, and one of my favorite things to do was to go out and dam this river. So within just maybe 30, 40 minutes, I would be able to stop the river from flowing just by putting nearby like tree stumps or branches inside of it. And that's because in mountainous areas like where I grew up, the rivers are really small, they're narrow. But as we go from the headwaters down to the mouth, our channel size is going to start increasing. These rivers are going to not only get wider, but now they're also going to get deeper as well. And part of the size is because the volume of water is also increasing. Again, we're not only getting wider, but these rivers are getting deeper, which means that as we move towards the mouth, this river is now holding more and more water, meaning that the discharge is going to increase. The amount of water moving through per second is going to increase just because we have a lot more water moving through the mouth than we do in our headwaters. And here, this chart is basically summarizing everything from the last slide. So we move from the headwaters, these mountainous regions where the river starts, all the way down to the mouth where the river discharges into an ocean. We're going to see that certain things, like the slope, is going to decrease. We're going to go from steep to gentle slopes. And we're also going to see that the sediment size is going to decrease as well. In our headwaters, these mountainous regions, we're going to have giant chunks of rock. That's going to cause really rough channels. But as we make our way down to the mouth, now we're looking at tiny pieces of dirt, basically that mud that we might see, and that leads to a very smooth channel. So as we go from our headwater to the mouth, we're going to see that our slope and the channel roughness decrease. But for our other factors, we're going to see that they increase from our headwaters to the mouth. So here in our mountainous areas, we have very tiny rivers. And then as they move to the mouth, they're going to get larger, they're going to get wider and deeper. So the channel size is going to increase, which means that the volume of water, just how much water is inside of these rivers, are going to increase as well, which will increase the discharge, or the amount of water moving through every single second. And I'm just going to go ahead and tell you, this is one of my favorite questions to ask on an exam. I want you to know how these different factors change between our headwaters to our mouth. You might not need to write a really detailed explanation, but always think about first the gradient. If you can figure out how the gradient changes, you can figure out how fast that water will move, what size the sediments will be, which will tell you the roughness and how quickly that water is going to flow. So here, again, I really want you to know the differences of how water moves from our headwaters where the river starts to the mouth where the river ends. When we look at our streams, though, it's not just water that's flowing through an area. These streams also carry sediment with them. And they don't only carry the sediment, but they're going to be able to erode as well as deposit sediment as well. So streams are going to be very important when it comes to erosion. And I've said this with probably every single chapter we've talked about so far. Everything along the surface of our planet is constantly being eroded or weathered away. And if you've ever seen a brown stream, like what we see here, this water just has a lot of sediment inside of it. And that tells us that that stream has eroded a lot of the channel around it. So when we look at our streams, we want to think about how incredibly powerful water will be. Even if we just look at a rainstorm, even though we might not think that a single drop of rain has a lot of power, in actuality, it does. So in this image, we're looking at a raindrop that has came and hit the surface of some sediment. When the drop hits the surface of our sediment, it's going to cause the sediment to move around through this backsplash. It's going to move the sediment as much as a meter, or about 3 feet away from where it was before the raindrop hit it. So within a single rainstorm, we can see a lot of erosion occurring, especially if it's just like a big open loose field. But we're going to see that when we look at our streams, because water is constantly flowing, it's going to be able to pick up or lift particles from the river's channel and then start carrying that sediment along with that water. So if we are looking at a stream channel that's just made out of a bunch of loose dirt, this means that it's poorly consolidated, just a lot of loose, broken material. It's going to be able to be eroded very easily. But if we're looking at a stream channel that's solid rock, now we're going to see less erosion because it's not just going to be able to pick up a solid rock. Instead, over time, it's going to have to break small pieces of that rock away through what's called hydraulic force. So rivers moving over the solid bedrock will eventually start cutting or eroding into the bedrock, but it's going to take millions of years to do so. So when we're looking at all of the sediment inside of our stream, there are going to be three different types of sediment. We're going to see that we have a dissolved load. And this just means that it's the sediment that is so small, it's actually been able to be dissolved inside of the water. So with this dissolved load, this is sediment that we can't actually see. It's invisible because it is so incredibly small. So this makes up a small proportion of all the sediment inside of our streams. What we're going to see instead that most of our sediment is what's called suspended load. And this is just sediment that's suspended or trapped inside of this water. Like we can see here in this brown stream. Here, there's just a lot of sediment that's being carried with the water. But usually the suspended load is going to be smaller sized particles like clays and silt, which usually just make up like a mud. But if we have a flooding event, we're going to be able to move larger particles than just those small clays and silt. Overall, this suspended load is the largest part of all the sediment within our streams. And then finally, we have the bed load, the sediment that's along the bed or the river channel itself. So these are generally larger sediments, things that are the size of sand, gravel, or even boulders. Now we're talking about larger pieces of sediment. When they're larger, that also means that they're heavier. So this water will need more energy in order to move, let's say, a piece of gravel than it would a piece of silt the size of like the ballpoint pen. So with our bed load, it only moves intermittently. This means that it's going to move a little bit and then stop for a period of time because we need very high energy water to move these larger sediments along the bottom of our rivers. So when we look at our streams, there are going to be two important things we need to consider. The first is capacity, and this is just how much sediment can the stream hold, just like I have a capacity for how much weight I can hold. But as we start increasing the discharge, that means that the water has more energy. And again, the more energy that I have, the heavier weights I'm going to be able to move. And streams work the exact same way. The more quickly the water is moving, the more energy it has. And therefore, it's going to be able to move a larger amount of sediment than a smaller, slower moving stream would. And this is also related to the stream's competence. Just how well can the stream actually transport different sizes of sediment? So if we're looking at like a gravel size sediment, here we're not going to see that a small river that moves very slowly is going to be able to move these gravel-sized sediments. But if we're looking at a flooded river that's moving very, very quickly, now it's going to have the energy to move these larger sediment sizes. Therefore, it's going to have a higher competence. So when we're looking at the sediment in our streams, we're also going to see that near our mouths, now our rivers aren't just eroding the sediment, but instead they're going to start depositing sediment as they get closer to the mouth. And that's because the closer we get to the mouth, the flow velocity is going to start decreasing. Again, the mouth, it's going to be a really flat area. So here, because it's flat, that water is not moving very quickly. It's slowing down, which means that that competence is going to be reduced. Now it's only going to have enough energy to move the small pieces of sediment and not those large chunks of sediment. So it's going to start dropping out or sorting these sediments. If it doesn't have the energy to carry a larger, heavier piece of sediment, it's just going to drop it. And this is going to deposit sediment along the sides of the river. And this deposited sediment is just called alluvium. And here we can see it in this image by this kind of lighter brown. So we can see where this river used to be in the past just by looking at the sediments that used to be deposited or be dropped out by the stream as the gradient decreased. and therefore the energy decreased, and the stream no longer had the energy to hold these larger pieces of sediment. So it just deposited them on the land. So when we look at our streams, we're going to have two overall types called bedrock streams and alluvial streams. And they're going to deposit and erode sediment very differently from one another. So when we look at our bedrock channels, like here on the left, we'll see that this river is moving over solid rock, which is why it's called a bedrock channel. This river is just cutting into this solid rock. But here on the right, we're looking at the other type of channel called an alluvial channel. And these alluvial channels are just made out of loose dirt. And these are the types of streams that we see more likely here in Florida. So when we look at our bedrock channels, these are most commonly found in the headwaters of our rivers, those really mountainous areas with a steep gradient. Here you'll see that even though it's called solid bedrock, we'll see that there are these large boulders or just large rocks sitting inside of the water. So here we see large sediment sizes. This is going to cause really turbulent water to flow through. The water is not only moving quickly because of that steep gradient, but now because it's moving quickly and kind of slamming into the rocks, it's creating turbulent, rapid waters. But in these mountainous regions, we're also going to see a lot of waterfalls forming, where the water is just going to hit along a cliff face and then fall straight down the side. Well, with these bedrock channels, we're going to see that the channel pattern, the size and the shape of the river is being controlled by the geology of the area. Basically, here the stream can only get a certain width and a certain depth because it's cutting into rocks. It's not going to be able to quickly erode these rocks away like we'll see happens with loose sediment. But our alluvial channels are very different. These are the ones that actually are composed of that unconsolidated sediment or loosely consolidated. So here just think about just dirt making up the bottom of these streams. Because the sediment can be moved around, it's constantly being eroded. It's being picked up from one area of the stream. It's being transported somewhere else where eventually it's going to be redeposited. So here the shape and the size of our river is just controlled by the sediment. Now because the river can move the sediment, the shape and the size of these rivers are going to change over time. So we're going to have two very common types of alluvial channels. One is called a meandering channel. Here, the rivers are going to meander. They're going to move back and forth on each other, kind of like how a snake will move across the ground by moving from side to side. And we see a lot of these meandering channels here in Florida. But the other type, a braided channel, is less common here. It's a lot more common in like an arid environment like a desert or along the bottoms of our glaciers. So when we look at our meandering channels, here we're going to see that the river is not just a smooth straight line, but it's curving back and forth upon itself. Again, just like a snake moving across the ground. So here, each of these little curves of our river is called a meander. And when we look at these meandering channels, we're going to have different areas where the sediment is going to be deposited or eroded away. So if we look at the outside of a meander, this is the side of the stream where we are going to see a lot of erosion occurring. So let's say that this river is flowing from the top to the bottom of this image. As it's flowing down, we're going to have water coming through and directly hitting the outside of the meander. Again, this is just loose dirt that's sitting along the side of our river. So if we have our stream bed and then water is coming through and colliding into it, it's going to keep eroding or pushing back this side of our meander. So we're going to see that the outside of our meander is always going to be eroded. But on the inside of our meander, because the water is not hitting it, instead we're going to see a lot of deposition occurring. That means that the water is slowly going to start depositing depositing the sediment that it's been carrying. So it doesn't matter which meander we look at. All meanders are going to have two sides. The outside part of our meander, we're going to see a lot of erosion. And this is called a cut bank because here the river is literally cutting into the bank or the side of that channel. But along the inside of our meander, this is going to form a point bar. Here, because the water is not hitting the inside of this channel, it's depositing all of that sediment behind. And we'll see these point bars on our next slide. But because each meander has one side, the outer side being eroded, and the inner side being deposited, we see that the meanders migrate or they move from side to side. So eventually, we're going to see that once this becomes so curvy, it's going to start curving along by itself. And eventually it's going to cut itself off. We're going to see that these meanders are now going to touch eventually. And water is very lazy. It wants to go the shortest distance possible. So if it can find a shortcut, water is going to take it. So if we get the meanders of our stream getting so close that they eventually touch, they're going to form what's known as a cutoff. Here, this meander is eventually just going to be cut off from the river. This means that the water is no longer going to flow this way, but instead, if these meanders here were touching, the water is simply just going to flow down like this, cutting off this meander and eventually forming what's called an oxbow lake, which we see here. So the reason that this is called an oxbow is because it's shaped just like a horseshoe. It tells us that our river used to meander through this area, but eventually those meanders got so close together that a cutoff formed. When it's just a cutoff, we have a small amount of water that's still flowing through the stream. But once it's an oxbow lake, we no longer have water flowing through. Instead, that water is just sitting within that lake. So here we're seeing an actual image of one of these meandering streams. And we can see that this river meanders. It curves back and forth quite a bit. So each little curve of this river is a meander. But we know that over time, along the outside of our meander, we have a lot of erosion occurring. But on the inside of our meander, here, we're seeing a lot of deposition. So in this image, we can actually see those point bars forming. We're having sediment being deposited on the inner side of these curves. And since we have erosion on one side and deposition on the other, these rivers are going to migrate. They're going to move over time. So if we were to fly over the Mississippi River in an airplane, we would be able to not only see where the Mississippi River is today, but we're going to see scars of where this river used to be. We can also see a lot of cutoffs occurring. Here, we're seeing that this stream is still moving through this cutoff, but it's only a small amount of water. If we allow more time to occur, if we come back in maybe 1,000 years, at that point, maybe this cutoff will be completely cut off, which means that water no longer flows through, but instead it's going to be sitting lake. And because it's shaped like a horseshoe, it's called an oxbow lake. But our braided channels are very different from those meandering rivers. Meandering rivers are there 24/7 and they're constantly full of flowing water. But braided channels typically happen in two environments. An arid desert kind of environment where you're only occasionally going to have water flowing through, or along the base of our glaciers where the glaciers are melting and now releasing that water as a liquid again. So these braided channels are really complex. Think about braided hair. You're going to have three strands that you're pulling in together and then separating again to form a braid. Here, these braided channels work in the same way. We have very thin, small streams that are converging together at points and joining each other, and then diverging or separating away. So with these braided channels, they're going to be very different from our meandering channels. Here, again, it's an alluvial channel, which means that it's just made up of a bunch of loose dirt. But because the water moves intermittently, in a desert, it doesn't always rain, so this river doesn't always flow. But the size and the shape of these braided channels is going to be determined by the sediment along the bottom. So if we have larger sediments, the water is just going to move around these larger pieces. Again, water is lazy. It doesn't want to put out the energy to move these larger pieces, if instead it can just simply flow around it. So we can see that here. We'll see these patches of land separating the different channels of a braided stream. And that's just because in this area, we're seeing larger pieces of sediment. But these braided channels are going to be very different. As you can see in this image, they're very wide. Sometimes these braided channels are going to be miles wide, but they are incredibly shallow. Generally, they're going to be a few inches deep. So with a meandering stream, they're also wide. The Mississippi River is over a mile wide, but it's incredibly deep. If you went swimming in the Mississippi, there's no way you could dive down to the bottom. But when we look at these braided channels, if you try to get inside of these, they might be a few inches thick. So you might be able to get your ankles wet, but there's no way you could actually swim inside of these braided channels. So when we are talking about our streams, we're also going to see some geological hazards occur, most commonly through flooding events. So we have all probably heard about floods if we've never even seen one. So a flood just happens whenever there's more water inside of a stream than it can actually hold. And again, that's the channel capacity. So if we just suddenly triple the amount of water inside of our river, we're going to have a flood event occurring. And floods are very unique because these are not only the most common type of natural disaster, but they're also the most destructive. We'll see that a lot of our weather-related natural disasters, like hurricanes or tornadoes, occur in very specific areas of the world. But floods, because it occurs from precipitation, happen everywhere, even in desert environments. So this is why flooding is the most common natural disaster. It's going to happen in every city, every state, and every continent on our world. But it's also incredibly destructive. Here in Florida, we build our houses and our other buildings to withstand hurricanes. They can withstand those 100+ mile per hour winds. But so far, we haven't developed the ability to build houses that can withstand flooding. So generally, if a building is flooded, we're going to have to go through and do a substantial amount of work to be able to save it. And in a lot of cases, those buildings aren't salvageable. If your building is incredibly flooded, it's probably going to have to be bulldozed and rebuilt. So flooding also causes a lot of economic damage as well. So we see that most of our floods occur simply because of the weather. We could have just really heavy rains or rains occurring over really large periods of time. But one thing that we don't think about is snowmelt. If we lived in Colorado, for example, every spring they have issues with floods because now this solid snow is melting back into liquid water and it's going to very quickly move through those mountainous regions, leading to flooding. So generally, most of our floods are flash floods. This means that they happen very quickly in a very small geographical area. It might have a flash flood in one town, for example, that's only going to last a few days. And these flash floods are controlled by how much rain fell, how long the rain fell, and what the surface looks like. As we talked about earlier, we're going to see that cities have a lot more problems with flooding than rural areas do. And And that's because cities have covered our surfaces with things like concrete and asphalt, where the water cannot infiltrate back inside of the ground. But in our rural areas, think about Kansas and all of that farmland. Here, not only the plants, but the ground itself are going to be able to absorb some of that water. So we see that in our urban areas, we have flash flooding being very, very common. And we'll talk about this more in a few slides. But we can even see flooding occur without substantial rainfall. So as humans, we figured out which areas of our planet seem to have a lot of flood. So we build these artificial structures in order to help limit flooding. But sometimes these structures fail. So we build dams to hold water back in a river. Or we might build levees to build up the sides of our rivers so that they can hold more water. But sometimes these dams and levees fail, which will themselves cause substantial flooding. So here we're looking at the prime example of what to not do during a flood. Here we see someone that's being rescued from their car because they drove on a flooded road. If you look at the statistics, the majority of people that die during flooding events are not people that drown in their house. It's people that get stuck inside of their car. And that's because water is incredibly heavy. If you ever just try to pick up a 5-gallon bucket full of water, it's substantially heavy. And think about the millions of gallons of water that will be in a flooded area. So here we can see that the flood water is reaching up to the sides of the door in this car. So we generally see that people that do decide to drive in a flood will get stuck in their car, even if it's just a foot or two of water. And that's because this water weighs so heavily and it's constantly bombarding against the side of that door. It doesn't matter if you're an Ironman competitor. Humans don't have the strength to be able to move this door against millions of water that is forcing this door to close. So this person likely tried to open their door, couldn't, and then began to freak out. So we can see here that they were rescued out of a window. So if you ever see a flooded street, don't ever drive down it. But if you do, and you do get stuck, don't take a minute to try to open the door and get out like we do every other time we get out of a car. You will never be able to push that door open. So we see that a lot of people get trapped inside of their car and then they start to panic. Habitually, we know that when we get out of a car, all we have to do is hit that handle and then step outside. When that doesn't work, we panic and we lose it. So if you ever are trapped inside of a flooded car, the only way to get out quickly is to roll out your window and then climb out. Here we can see that there's something covering the window. Likely, this car lost its power once it started moving through these flooded streets. So if you have an automatic window, you're not going to be able to roll down your window. Instead, you're going to have to break that window out, cover it with something so you don't get cut, and then escape. But again, just don't ever drive down a flooded road. But as humans, we like to try to control flooding. It not only causes a lot of deaths every year, but it also causes a lot of economic damage. So we try to build structures that will limit flooding. We can build artificial levees, and we can see one here on the left. When we take a normal stream and then we build levees, what we're doing is we're building up the sides of those river channels. Overall, this means that it's going to be able to hold a larger volume of water. Therefore, if it can hold more water, it's less likely that the water is going to be able to go over the sides and then flood the land around the river. We can also build dams along our rivers. So here we can see a river that's been dammed. The water is going to be held behind the dam, and then this dam is very slowly going to release a specific amount of water every single day. And then finally, what you're going to see a lot of in urban environments is something called channelization. And these are basically artificial streams that are created by humans. Here we're going to go through and we're going to pour concrete along the sides. This is going to create an artificial stream that's going to quickly get water out of an area. And we see a lot of channelization in urban environments, again, because we have a lot of our surfaces covered in asphalt and concrete. Water is not going to be able to infiltrate through those surfaces. So instead of allowing our cities to flood every single time it rains, what we do is build channels. And you'll see a lot of channels near our campus. But there are issues with these man-made flood control devices. So even with these artificial levees, where we've built up the sides of our rivers so that they can hold more water, when these artificial levees break, we're going to instantly release all this extra water into the land around it. And this is one of the reasons why Hurricane Katrina was so devastating to New Orleans in the early 2000s. That's because New Orleans sits below sea level. So in order to keep all of this water outside of the city, they built artificial levees surrounding the city. But during Hurricane Katrina, it damaged the levees. They failed or they broke, and it instantly allowed all of that water being held inside of the rivers to enter the city, causing substantial flooding and massive loss of life. But we can also see our dams failing as well. One of the largest examples was from the Yangtze River in China. It broke and it killed hundreds of thousands of people within a matter of minutes. So although we build these structures to help control flooding, sometimes when these structures fail or they break, they themselves will cause flooding. But now we're going to move into groundwater, the water that's stored below the ground on our planet. So if we could dig down below the surface, we're going to find groundwater. And groundwater is just water that's going to be in all the little spaces between pieces of sediment and in the narrow joints and the breaks inside of the rock that sits beneath our sediment. So if we were to go outside in our yard and start digging with a shovel, underneath that grass, we're going to find a layer of sediment. And if we dig down deep enough, and especially if we do this right after a rainstorm, we're going to find a lot of water in that sediment. But if we just keep digging farther and farther, eventually we're going to be below the sediment and hit solid rock. Although that rock is solid, it's full of a lot of little fractures where it's been broken. And inside of those fractures, we will also find water. So groundwater, again, it's just all of the water that's stored beneath the surface of the earth in either sediment or in rock. So groundwater is actually the largest reservoir of fresh water that's accessible to humans. So the largest freshwater reservoir is glaciers. But if we were to get all of our drinking water in our county from, let's say, the glaciers of Antarctica, our water bills would be outrageous. I don't want to pay for our government to go to Antarctica, get massive amounts of ice, melt it, and then bring it back for me to drink. Instead, I want my water bill to be cheap. So we want to get fresh water that's accessible or readily available. So most of the time, our drinking water comes from groundwater. And we see that about half of the worldwide population uses this groundwater for their everyday drinking water. But we're going to see that with groundwater, it's very easy to overuse it. So we've already learned that the ground can only hold a specific amount of water. So if we start taking out too much of the water, we can cause depletion. We can run out of that water. But we can also see issues like pollution, contamination getting inside of our water, as well as pumping costs. But especially here in Central Florida, our groundwater can have a major geological role, especially from forming sinkholes. And that's because in Central Florida, almost all of our rocks are limestone. And in our first couple chapters, we learned that limestone is made entirely out of that mineral calcite. And one of the most important things about calcite is that it dissolves in acid. So with rainwater, it's naturally acidic. It's not acidic enough to burn our skin, but it's slightly acidic. So that means over long periods of time, all of the water moving through the rocks beneath our ground is slowly eroding those rocks away, just like a drop of acid erodes calcite. So because all of the rocks in Central Florida are made out of limestone, and all rainwater, regardless of where you are, is naturally acidic, as that rainwater infiltrates into the ground, it starts eroding these rocks. And eventually, it's going to start forming caves or large cavities in the rocks. And if those caves get large enough, eventually a sinkhole is going to develop. And this just means that once we have the cave, once it gets big enough, here the top of the cave is simply just going to collapse in, and it's going to form a big open sinkhole. Some of these sinkholes are large enough to swallow multiple houses at a time. But when we're looking at our groundwater, all of it comes from infiltration. It's this water that's soaking or being absorbed into the ground from rainfall. And we've already talked about how infiltration and runoff depend on things like the slope, how steep the ground is, as well as what it's covered in, whether it's natural materials or man-made, and the types of vegetation that we see. But when we look at our groundwater, we're going to have two different zones. At the bottom, we're going to have our zone of saturation, and then on top of it is going to be our unsaturated zone. So when we look at our zone of saturation here at the bottom, here every single pore space, each gap between pieces of sediment, or every hole inside of the rock is going to be 100% filled with water, which we call saturated. So when we look at this image, we'll see that this zone of saturation is shaded blue. And that means that every single space within this zone is saturated or completely filled with water. On top of it, we have the zone or the unsaturated zone. Here we can have some water in these pore spaces, but not every single pore is completely filled with water. So we call it unsaturated. We always see that the unsaturated zone sits on top because gravity is constantly pulling water down farther and farther below the ground. So gravity is going to be pulling the water down until eventually every single pore space in this zone of saturation is filled. So we're going to see that there is a dividing line between our zone of saturation and the unsaturated zone on top of it. And this dividing line is called our water table. Overall, it has a very irregular shape, but it kind of mimics what the surface of our planet looks like. Here we'll see that there is a slope going down towards the center of this image. And if we look closely at our water table, it also goes down, but it's subdued. Instead of having a steep slope, it's a more gentle slope. But just like water flowing down a hill, we see that groundwater also flows downwards. It's always going to move from higher elevations down to lower elevations. But we're going to see that whenever our water table intersects with the surface of our planet, we're going to see streams or rivers starting to develop. The book describes this as water piling up, but I've personally never been able to pile up water like I have a stack of paper. So what I prefer instead is to think of the intersection between the surface of the earth and then the water table beneath it. If we have, let's say, the surface of the earth, we have a valley here. If our water table comes through and intersects, everything below that water table is going to be full of water. So here we're going to have a stream developing in these low-lying valleys. But the amount of water is going to depend on how much rainfall we've had. If we have a very rainy season, like we're having during our summer months, we're going to see that this water table is going to increase. It's going to go closer to the surface because more water is going to infiltrate into the ground. But we also can see that our water table can fall. It can get lower if we have a drought. So if it just doesn't rain for months at end, that water is not going to be able to infiltrate into the ground, and therefore the amount of water is slowly going to go down as well. So when we look at our groundwater, there are going to be two important things that determine whether or not we can drill inside of them to get drinking water. And these two important factors are porosity and permeability. So with porosity, this is just overall the amount of pore space, or just little holes or spaces between either different pieces of sediment or holes within the rock itself. So the porosity is just the percentage of open space within a rock or a sediment. So if we look at a rock with a low porosity or low pore space, this means it can only hold a little bit of water. If we look at a rock with a high porosity, where we see that there is a lot of pore space between each grain, now this rock is going to be able to hold more water. So if we wanted to drill inside of these rocks to get groundwater, if we wanted to pump up that water so that we can have water coming out of our taps, we always want to drill inside of a high porosity rock because it can hold more water than the low porosity rock. But we also want to look at permeability. And permeability is going to be related to porosity. But permeability is just how well can water move through from one pore space to another. So here on the very left, we can see that these pores are all very well connected to one another. So that means that if we drilled straight here, once we start removing the water from this pore, water from these other pores are going to come down and replace it. It's going to be able to flow from one pore to another, which is called a high permeability. But if we're looking at tiny pore spaces, we're going to have low permeability. The water is not going to be able to move from pore to pore. So if we were to drill into one pore here, once we start pulling up the water, it's very quickly going to go dry. So when we're trying to drill for groundwater, again, we want high permeability and high porosity. We want those rocks to have a high porosity so that they're holding a large amount of water. But we also want those rocks to be permeable. I want the water to be able to pour or be able to flow from one pore to another so that once this pore is dry, it's going to be refreshed from these other pores. I'm not going to quickly run out of water and have to drill a new well. So when we're looking at groundwater, we're going to have different types. When we're looking for groundwater, we want to drill inside of an aquifer. And these are going to be rocks or sediments that have high porosity and a high permeability. We want that rock to hold a lot of water, and we want that water to be able to move through the rock. But we also have things called aquitards. Here we have clays. We have sediments that are tiny. So this means that there's only a little bit of water trapped between each piece of clay. It has a low porosity, and it also has a low permeability. The water is not going to be able to flow from one pore space to another. So an aquitard basically means that the water cannot flow through. It's going to be trapped inside of that rock, while an aquifer, the water is going to be able to very quickly and easily move through. So when we look at our groundwater, we see that it slowly moves. Again, just like water on a hill, water moves from higher elevations to lower elevations. We're going to see that the groundwater is going to move in the exact same way, always from high to low elevations of our water table. This is because gravity is just constantly pulling it down. But groundwater is going to move much more slowly than, say, a river does. Rivers are moving likely miles, if not just feet per day. But when we look at groundwater, it moves incredibly slowly. We're talking about maybe a few centimeters per day, but it still flows. But the deeper that we go in our zone of saturation, the more pressure there will be. So this causes water to not only flow from higher elevations to lower. As this water gets deeper, it's under more pressure. So this water is going to kind of curve to these lower elevations because of changes in pressure. But again, we're going to see that when the surface of the earth crosses our water table, we will always have a stream or a river developing. So since we use groundwater so extensively for our drinking water, we also want to think about some of the environmental problems associated with our groundwater. So for the most part, groundwater is at equilibrium. If we never drilled to take out groundwater, it would stay the same year after year. But since we do drill inside of these rocks so frequently to get drinking water, we cause imbalances inside of our water table. So just naturally, we can see our water table rising if we have more rain, or we can see it lowering if we have like a drought. So in addition to just periods of rainfall or drought, we can see issues with groundwater, and especially with where our water table is, based on how much water we take out of the ground. And this can be major issues in places where we use a lot of irrigation, especially in farmlands. It takes a lot of water to water our crops. So we'll see in a couple slides that in very rural farmlands, we're going to see that even though there aren't a lot of people, we still have major issues with groundwater because they're taking so much water out of the ground that that water table is going to start lowering. There's just going to be less water available. So here we can actually see where farmers have irrigated their crops. We can see them in these very vivid green circles. And this is because there are these long arms that go off and then spin around, watering all of the plants underneath them. But right now, our technology for watering our plants is not very great. What we do is we cause that water to just go up into the air. And we know that water inside of our air is very easily evaporated. It's going to change from liquid water into a gas form of water very quickly. So our current ways that we irrigate our crops are not very efficient. While we put a lot of water out, only a small amount of water is actually going to be absorbed by those crops. So here we're looking at a map of an aquifer, this groundwater that goes all the way from South Dakota down into Texas. This is also an area where we get a large amount of our food being produced in the United States. But these crops require massive amounts of water, which means that these farmers are not only putting a lot of water into our air, they're also pumping a lot of water out of the ground. So we see that we run out of water in these areas, which could be a huge issue in the coming decades. If we continue to run out of water, how will we continue to water our crops to have food in order to eat? When we start lowering our water table by taking out too much of the groundwater, in addition to just running out of water, we can also see something called land subsidence developing, where the land itself is just going to start subsiding or sinking down. And that's because when we are looking at that zone of saturation, all of the holes in that rock or sediment are filled with water. Once we remove the water, that means that the rock is full of air, and the weight of the rock above it is going to start compressing down, causing the surface to look like it's sinking. And this is going to be a big issue in areas where we just have a bunch of thick layers of loose sediment, especially out in California. So if we look at this image here, we see this pole with numbers on it. These numbers are years on where the land surface was in that year. So if we look from 1925 down to the 1970s, we're talking about 50 years. Here, the ground subsided or sank down 30 feet. This is going to cause substantial issues, especially if it's built in an urban environment. Think about not only our houses, but our roadways and bridges suddenly sinking down 30 feet. And all of this is due to overpumping, taking out too much groundwater too quickly. But we also need to think about contamination. Because this water is stored underground, if contamination or pollution gets inside of our groundwater, it's very difficult to get that contamination out. And there are a lot of different common sources of contamination within our groundwater. And some of the major ones are just septic tanks. In older neighborhoods, and especially in more rural areas where houses may not be connected to the city's sewage system, they'll use septic tanks. There are these large tanks that are put generally underground, and everything that you flush down the toilet is going to eventually make its way to the septic tank where bacteria is going to kind of eat it away. But there's a major issue with septic tanks because once they are a few decades old, they begin leaking. And this is a major issue because think about some of the stuff you flush down the toilet. I personally don't want it leaking out into the sediment around my septic tank, especially if I have well water. If I have a well in my yard where I pull up my own water. If my septic tank is leaking, that means whatever it's leaking, including some of that fecal bacteria, can make its way into my drinking water, which can make people incredibly sick. But we also want to think about farm waste. With our farmland, we commonly use manure. With manure, it has very high nutrients inside of it. So if a farmer puts manure on his crops, the next time that it rains, the rain is going to run off their farm. It's going to take that manure with it. So about 3 years ago, Lake Okeechobee, that giant lake in the center of Florida, turned a Nickelodeon slime color of green. And that's because that year, farmers put way too much manure on the surfaces of their crops. And we know that in Florida, during the summer, it's our rainy season. So with a substantial amount of rainfall, it took a lot of the manure from these farms and washed all of those nutrients into the lake, allowing algae to just go crazy. So much algae grew that it not only turned the entire lake lime green, but the lake itself had surface waters that were the same consistency of that Nickelodeon slime. So our farming has issues not only with taking out too much water, but we also see some issues when farmers put too many nutrients on their crops as well. So in some areas, once we start polluting our water, we can treat it, but treating our water to get all that contamination out is very, very expensive. So while it is possible, most of the time, if we have another water source available, we're just going to abandon that groundwater. So if we get a lot of contamination below the ground, now we might start pulling our drinking water from the river instead. But that means that all of the water below our ground is going to remain contaminated, which can be an issue for future generations. But one good thing about living in Central Florida is, again, all of our rocks are limestone. And here, this limestone is kind of a double-edged sword. It's bad because our rainwater is acidic and over time eats away the limestone. But limestone also has some major benefits because limestone acts like a natural filter. Think about like a water filter, like a Brita filter that you might have in your fridge. When you pour the water in from the tap, it's going to move through that filter and remove the contamination. Here, limestone naturally does that. As our groundwater moves through limestone, the pore spaces within the rock itself is going to capture that contamination. The contamination is going to stay in the rock, but the water is going to be able to continue flowing through, getting cleaner and cleaner as it goes. But in areas without limestone, we don't see this occurring. If we have contamination coming from a septic tank in an area without limestone, so any other type of rock, that contaminated water is just going to keep flowing. So everyone Farther down from your septic tank would be drinking all of that horrible bacteria leaking out.